Hello, my name is Divar, and I will be explaining my problems for the evaluation period 1. First, we have chapter 2, problem 14, which tells us that our equation 30 sin 2 times t plus 50 should be converted into sine and cosine components. So here we have our equation, and we use this formula: sine A plus B equals sine A times cosine B plus cosine A times sine B. We then substitute our values in to this equation, which gives us the following. Then we substitute it, giving us this simplified version. From here, we just calculate what cosine 50 and sine 50 is in degrees, as the problem explains to us that it should be in degrees, giving us these values. And lastly, we just multiply 30 times this, 30 times this, giving us the answer: 19.284 sine of 2t plus 22.98 cosine of 2t. I then took this equation, put it in GeoGebra to get a better look as a graph, and we get this graph, which follows the sinusoidal waves that we usually get with sine and cosine. Next, chapter 3, problem 16, which we need to find the DFT of the signal shown below, which is this graph. For this graph, we find that the period would be equal to 7, and that our interval would be from -3 to 3, which is our values here, which goes from -3 to 3. Next, we implement these values into this formula given to us by this example. We substitute here where it's n to the x to the n, and we get this long function. And then we then simplify it further till we get to this point. And as you can see here, this would become 0, as in 1 times 1 minus 1 to this 0.5. These would cancel out and become 0. But in order to not get that, we use this function, e to the j of degree equals cosine degree plus j sin to the degree. And we would get this equation, leading us to this final answer of 2j sin times 4 pi m divided by 7 plus j sin times 2 pi m divided by 7. Next, we, in order to get our values, as we need the period of n to get to 7, we use MATLAB. And first we implement our values, we write our period, then we put our formula here in order to get our values, and we graph it. As you can see here, this is the values that we get, the numerical values. And as you can see, x to the n would have given us 0, as we had shown before, as the values canceled out. But interestingly, we get one value that it's real and one imaginary values in all of these numerical values. Lastly, we get our graph here, which would give us the magnitude of DFT. Last problem, chapter 4, problem 12. Here we use sig noise to generate two arrays, one of 128 points and the other 512 points, having frequencies of 320 and 340 hertz. We use these to calculate a plot and power spectrum. So here is the graph. As you can see here, these are our values. First, the 128 of the array and 512 of the other array. These basically would be implemented as this has a higher resolution, I guess you could say, a better view, and this is the worst one. We use this function to plot our frequencies, so we would get our samples of 128 and 512. We also use the Fourier equation here to get our frequency components and their powers. Lastly, we plot them, and this is what we get. This would be the lower resolution, I guess you could say, and this would be the higher resolution, showing the differences, even though they're made of the same frequencies. And thank you. Those would be all the problems.